And I need to log on to this one too. Let me make this happen. Good. Continue. Cancel on that. So just a little housekeeping thing. Maybe I'll put an announcement on this as well. When people send in their homeworks, and I apologize, I'm still behind on grading them, so I'll get to those and get you last week's hopefully the next day or so. When you upload, it would be helpful to me, even if on the first pass you decide you're not going to make any revisions. It'll be helpful to me if you just re-upload the unrevised homework from the first one, even if there's two identical copies. Otherwise, when I see it's not there and I have to check back and see that you put the one in before. So if you can, that would be great. Good. Let me share my screen over here. Get this running. Okay. Get notability up here. Excellent. Okay. So support vector machines. This was more of the work of Vapnik and Chervonenkis, the same guys who came up with the VC dimension. These are essentially very theoretical computer scientists and mathematicians. So this is a very theoretical computer science-y kind of algorithm. It has a lot of, it gets a lot of press and playtime because it's very, it's understandable and it makes sense. And in some cases it can be very fast. I have to say, personally, I don't like it very much because I think that it's not really a learning algorithm in the classic sense. These are the algorithm for support vector machines basically assumes you have all the data at once. It's a batch method. But when you, so it's a batch method for training these things. There's no, people have worked on it, but there's no official iterative method. You can't take samples as they come in one at a time and come up with the best estimate based on all samples in the past. There have been some approximations for that, but for the most part, they assume you have all the data at once, and then it constructs a feed-forward network that gets you a decision boundary. Its real advantage is that those feed-forward networks are in some sense as small as possible. And so that is a value to this because it sort of says the training is complicated, which is not training really, the construction is complicated, but the use is very simple. And that's often the way things are with machine learning. That's what you want, is once you've sort of learned the thing, now you want to be able to perform very quickly. So the learning stage will be slow and the performance stage will be fast. But if I give you another data point, you have to retrain the whole thing. There's no way of sort of incrementally adding a new data point into it. So it has its pluses and minuses. I think the real value of this is it's a good way, as Haken does, to introduce the concepts of constrained optimization, which are worth being aware of and will be helpful as we analyze some of the other algorithms that we're going to get to in later stages of the book. The math behind this is based on the math of Lagrange multipliers. Some people are going to be familiar with it. Some people aren't. I don't know, for the people who do know about it, you probably had the same experience I did when you learned this, which is you just kind of memorize it and you do it and you're sort of amazed that it works, but you don't actually have a good idea of why it works because it just seems sort of both brute force and sort of a mixture of very, very clever and very, very stupid at the same time. And it's hard to imagine this thing would work. So I'm going to try to motivate a little bit of why it works and give you a little bit of a sense of that. But I think it's, really feeling comfortable with the Lagrange multiplier method for constrained optimization takes a lot of thinking and a lot of practice, and you just have to do it a lot until you get the hang of it and it starts to make some sort of intuitive sense. This chapter is very dense, and so I'm actually going to go through just using Haken's structure, a lot of this, and stay a little bit more close to that. People I'm not going to go through so the homework problems ask you to do some fairly straightforward things on this, and if people have questions about that, we can talk about it afterwards, but hopefully the lecture will give you enough of the background on this. So the first thing, support vector machines basically are the same concept as a perceptron. So let me get this thing up and running here. let's see, I'll do it with black ink. So you know, this is what the this is what the network's going to look like, right? It's going to be some kind of decision surface where the function sigma of x is basically some kind of a decision boundary, or actually more usually it goes from -1 to +1. And so that you're going to, or sigma of W transpose X. So the idea is you're just trying to classify things. That's the simplest version. You can do it for continuous functions, but it's much easier to understand these things in the decision boundary. So it's that you're building a perceptron. That's all you're going to do, right? And this thing has more or less power depending upon whether or not you use basis functions for it. So eventually we're going to do a basis function perceptron where we say y equals sigma of W transpose of phi of x times phi of x, where this is a vector. So eventually we're going to have a structure that looks like that. But in the end, it's just a perceptron. And so that could be thought of as, you know, either x comes in multi-layer and I have my W here, and then this goes through some sigma function and I get out a plus or minus 1. Or it could be that x comes in down here and I have some, you know, this is phi of x, some nonlinear transformation. So that's the structure of these things. And the question is, can we train this in some interesting way? And even more importantly, can we train this in a way where we might be able to get rid of some of these hidden units and make a smaller network out of it? And that's the motivation behind this whole thing. But in the end, it's just a binary classifier method. And what the intuition that Vapnik and Chervonenkis came up with for this is that when you're looking at this hyperplane, if you're trying to separate, you know, the square boxes from the circular boxes, and then the it's interesting. Don't need that. Then all you care about are the ones that are close to the boundary. Sorry, I don't know why sometimes this thing decides it's going to do weird things to me. So all you care about is this separating boundary, and what you want is that separating boundary to be as far apart to make as much distance as you possibly can. Now, you could ask, why do you want to make as much distance? I mean, what do you care whether it's 0.1 or 10 or 100, right? If you can separate it, you separate it. And that's a perfectly valid point. But whatever it is, whether you put that line here to separate, or you put it here to separate, or you sort of make it diagonally through the middle like that, the key thing is the only points that matter are the ones that actually are very close to that boundary. The points out here, these guys, these people, don't actually affect where the boundary is. You only care about the ones that are right near the middle. And that was the key innovation of this, which is that at some point you only have to pay attention to these guys who are right on the boundary. And then you could say, okay, well, let's try to be as far from all of those as we possibly can. That sort of makes sense if you think maybe there'd be some noise at some point. let's allow for noise. But in fact, this model there's no noise assumption in this model. So that, again, this idea that being as far as possible is sort of it's a self-imposed desire on this thing. But that's important because when you think about these guys only on the boundary being important, that means that potentially things could be a lot faster. That when you know, in the end, if all you have to do is find W transpose X, W is W, that's not going to matter. But it's going to matter a lot once we start looking at W transpose phi of X. Then all of a sudden you're going to find, because you have to decide how many of these basis functions are there. And it's going to be possible by only looking at the samples on the boundary to use fewer basis functions. So it's as if you're, instead of thinking about pruning the basis functions, what you're actually going to prune is the data set. Because if I gave you this entire data set, you know, here's your full data set, right? But I then decided to delete all the ones off the boundary, right? If I deleted those points, you get the same answer. So in theory, your training could have been much faster, right? In practice, you still need to know how close you are to the boundary in order to know to ignore those data points. But in theory, it could be much faster. And in fact, if you just wanted to save the important data points in memory, you could do that. So that's why this stuff becomes important, and that's a lot of what this is about, is how can we ignore data points that don't matter in some way. Okay, so now on to Lagrange multipliers. So the idea behind Lagrange multipliers, this is what, and so now let me back up a second, because the point is that this is going to become a constrained optimization problem in order to find those points, but I haven't told you yet why that is. So but first we're going to look at constrained optimization and how you do it. There's a number of different ways to do it. Lagrange multipliers is only one. And usually we have some function f of w, which we're trying to minimize subject to some constraint, e of w less than or equal to 0. And a typical kind of situation would be that, and in the case I'm using w because of the weights, often we'll use x, who knows. Let's suppose that w, you have two weight values here, w1 and w2, and then you have, and this is your looking down on your cost function, right? So the minimum one would be right in the center. But what I say is actually I want to constrain so that I'm only willing to accept values that are on this line, or maybe on this side of this line. Okay. Now, let's start first with just the values on the line. So I'm saying now, okay, I'm only going to accept values that lie on this line. Well, so intuitively, where's the right answer? The right answer is going to be there, right? And in fact, if you were to look along this line and plot the values of the cost, so this is going to be j of w, some kind of cost. If I were to plot the values on that, I would sort of see that j of w would go down and come up like that, right? Sort of looking down, right? That is just because here's a higher cost, I'm going out to these contour lines of the underlying cost, right? You have to, hopefully you can see that I'm sort of trying to do this in 3 dimensions in some way. This line here is intended to be coming up toward you in some way. But the point is that there's a minimum cost along that line, which has something to do with the underlying, this underlying cost function here, right? And so at one level, that doesn't seem very hard, right? You could kind of walk along that line and say, okay, where is this? But this gets very hard in higher dimensions. And so the Lagrange multiplier method is a clever way of trying to do 2 things at the same time: minimize the cost, but stay on that line. Now, another way to think about and we'll look at that in a second. Another way to think about this, though, is that if I have a line like this, and I have a point, and I want to say what's the closest point, where on this line is the closest point to that point, it's going to be this here. And the closest spot on the line is determined by the point where I make a right angle to that line. And hopefully you guys all remember this from geometry, and we've talked about this before. And it's basically because the triangle inequality, right? The triangle inequality says that this distance is always less than the sum of that plus that. Okay. So if I look at the sum of this segment plus that segment is always going to be greater than this segment. And that's just the triangle inequality. So in any vector space, or for that matter, in any norm space, you have the triangle inequality. And in any vector space, the correct answer is always going to be that this thing is a right angle. So basically what we're looking at is kind of the same thing. So now if I said, okay, what's the closest point on this line to the minimum cost point, it's going to be the point at which that is perpendicular. Okay, but I drew this as circles. Now let's draw it slightly differently. Let's draw it as if it's, suppose I have my cost function looks like this. And now I want to find the closest point on this line, okay? Well, it's pretty clear it's not that, right? It's not the perpendicular distance anymore, right? It's actually kind of going to be here, because you see that sort of fits on this inner circle a little bit better, right? It's that point. So what is this point? How do we define that point? Well, locally, if I were to blow that up a bit, we have this line here, and I have a cost function. I have my basic cost function that's doing that. Locally, what you'll notice is that they share a tangent. Right, so the tangents go in this direction on both of them. So the tangent, and more importantly, they sort of share what you consider a gradient, right? The gradient of the cost function will point perpendicular to these cost function isolines. And if you say we want to be on this line, but it costs me money to go off this line in some way, then the gradient of that cost is off here too. Goes off to the side as well. So now I can say, okay, I want to find the point on that. So it's going to be the point where these two gradients line up. And so you could say, okay, we're going to do something like that. Therefore, I want in some sense, the gradient of the cost to equal the gradient of my constraint, right? That's kind of what I want to have happen. I want to find points where the gradient of the cost equals the gradient of the constraint. Yeah. And again, this is in some ways very similar to the concept in just regular one-dimensional calculus, right? If I want to find the maximum of some function like this, I find points where my tangent is 0, right? But what's the significance of 0, right? Why do we find, why do we set d f dx equals 0 to find a maximum or a minimum? Well, what's a maximum or a minimum? It's the height above 0, above that line, right? So I'm trying to find the point where this cost, how high I am, is perpendicular to the function that's moving along this way, right? In a calculus problem, the height is the cost and the function is the constraint, right? I must lie on this function of x. What point? But I want to find the highest point. That's the thing I'm trying to maximize is height. I'm trying to maximize the height subject to staying on the line f of x, on the curve f of x, right? So what happens there is I find the point where the gradient of the cost, which just looks like this, right? The gradients of the cost functions are the isolines of the cost are just parallel. The gradient of the cost always points straight down. The tangent of the cost always points like that. So I need the gradient of the cost and the gradient of f of x to be in the same direction, right? So this is just a generalization of the concept that happens in regular calculus, right? Calculus is all about optimization. It's all about finding extremal values of functions. So this is a generalization to finding the extremal value of a function, right? It just says instead of operating in a nice, sort of square axes, I'm operating in this space where I have these sort of circular, or some could be a very arbitrary shape cost. And this constraint doesn't even have to be a line. It could be a curve, right? I could have a constraint curve. That's perfectly fine, right? This could be, draw like that. And the answer is still the same. It's still the point at which the curve and the, I'm trying to get this back to black somehow. The curve and the cost are orthogonal to each other. So again, if I were to blow that up in this, I could have a curve here coming down. And it's the same thing. I find the point at which the curve and the cost function, my constraint curve and my cost function, are both, they both have the same tangent at the same time. And that's always going to be an extremum. It may not be the best extremum, right? There could be other places, right? Suppose this curve comes back around like that, right? I could have another point at which some other line becomes tangent, right? And then this becomes a candidate point. Which of these is better? Well, this one's better because it's closer, right? It's on sort of the inner curve. This one's on an outer one, right? But you didn't necessarily know that. So these are just extremal points. So just like in calculus, there may be more than one spot at which you have tangents of 0. Right? Just in Lagrange multipliers, there may be more than one spot at which you have a candidate extremal point. If it's a line and this is convex, meaning that this thing basically looks like a circle, and you're looking at lines coming down, there'll only be one point. But in general, you can't assume that. Okay? It turns out for these support vector machines, there's almost always just one point. So you, in fact, for everything that will matter to you, there will be exactly one solution. But again, in Lagrange multipliers in general, there doesn't have to be. So this is the context that we're working in. Okay, now how did Lagrange multipliers actually make any of this stuff happen? What we do is we do something, possibly one of the stupidest things you could ever do, is you just add the two functions. So here, so take this example. We're going to minimize x squared subject to x greater than or equal to 1. Oh, let me, so what about this greater than or equal to, right? Because I could have just said, let's make x equal to 1. And you'll notice that nobody seems to care if it's less than or equal to, greater than or equal to, or equal to. It doesn't seem to matter to anybody, right? Why does that not matter? Because all the interest of any solutions almost always lie on the boundary. If you look at a, again, if we look at this kind of situation here, the solutions will always lie on this line. If I say, okay, I'm willing to be greater than that line anywhere on this side of the line, it's always going to be the closest point. Otherwise, it wouldn't really be a constraint. Like the answer is never in the middle of this zone, right? It's because suppose it were. Suppose that we had a situation where I said, okay, here's my cost function, and I want to be on this side of this line. Okay, well, there's the answer, right? So that's not difficult. So any hard problem, the answer is always going to be on the line. Anytime the optimal answer is not on the line, it's not really a constraint. You're not dealing with a constrained problem. Okay? This is going to become important because some of these constraints are things that will be easily satisfied. For instance, back to here, once I've picked this line, once I've chosen this optimal hyperplane here, smaller, once I have that line there, then I can give you as many points as I want out here and as many points as I want out here, and they don't matter. We're already optimal, right? But if I give you a point here, or even worse, a point there, right? That says I have to move this line. That becomes an important constraint. So there are constraints that you don't care about because the optimum's already satisfied, possibly because you've satisfied it already because of some work, possibly because it just didn't matter, right? I mean, suppose that we went the other way. I just pick a line in space, right? I just pick a line, start throwing examples at it, and lo and behold, by magic, all the examples just automatically fall on either side of that, right? So I'm saying, okay, I'm going to constrain this line based on all those samples. Not much of a constraint, right? I already have my answer. I picked my answer. You know, I've got my answer right in the center, and I'm very happy with my answer. And you know, along come a bunch of constraints that say, okay, you got to be on this side of this line, and you got to be on that side of that line, and you got to be on that side of that line. You say, fine, good, no problem, right? I got it. So the only cases that matter are the cases when it's the other way around. You say, okay, now you got to be on this side of this line. It's like, oops, now I'm going to have to go here. And it's always going to be on the boundary. Yeah. The situation when that doesn't quite happen is suppose that I have a bilobed function. Suppose I had something that looked like this. I've got two peaks. And I say, okay, I want to be on this side of this line. This is now in a one-dimensional case. Okay, there's my peak. But now I say, okay, I want to be on this side of this line. Well, there's my peak. It's not on the boundary, right? So, it could be, so things like that can happen when you have things that have lots of peaks in them. But for almost all of the network structures we're going to look at, that's never going to happen. Okay, back to, so we're going to take the simplest possible case, minimize x squared, just one dimensional, just a scalar, subject to x being greater than or equal to 1. And remember, the answer is going to be on the boundary, so is it greater than? Doesn't matter. Okay. So here's what Lagrange multipliers do. You set your cost function, instead of just being x squared, you add this extra term. You add this value lambda, and you multiply times something, right? Now, this is a constraint, and what that constraint means is we want, you know, since x is greater than 1, what we basically want is we want 1 minus x greater than 0. Okay? So you want 1 minus x to be greater than 0. So you just take 1 minus x and you multiply it by lambda, right? So what are we actually doing? For all positive values of lambda, anytime if x, and again, it doesn't much matter if it's positive or negative, but you can think of lambda as sort of penalizing how far off the zero you are in some sense, right? So in this case, I want this to be small. I can make this small by making x very big. As soon as x gets greater than 1, well, it should be perhaps to make this make more sense, I should write this as negative. It's not going to make any difference. But if I wrote that as, let's suppose we wrote this as lambda times x minus 1. So if we did that, then if x gets very big, this thing gets very, very, I'm sorry, I'm getting it backwards. I do have it written right. Apologize, get myself all confused. I told you this stuff is confusing. What this says is x being big is fine, right? If x gets big, this thing goes negative. That thing being negative makes j small. I'm happy about that. But as soon as x becomes less than 1, this stuff starts getting positive and will cause a penalty, right? So what I'm going to do now is I'm going to say, okay, well, what we're going to try to do is we're now going to optimize with respect to both of these things. How do we do that? We use the Kuhn-Tucker conditions, which are down here, okay? So you have these conditions, you take the cost, and he wrote it as 2 conditions, but really the only one you care about is stop that, please. Need that to go away. You only care about one of them. So you're going to take the derivative of the cost with respect to the weights, or in this case with respect to x, and you're going to set it equal to 0, right? But now you see what you've got here is it's this augmented cost function, right? I added this extra term to it. Right? So it's got these 2 terms in it, and I'm going to look at that. And the first thing I'm going to do is I'm going to take the derivative of the cost with respect to x, and I can figure out what that is 2x minus lambda. I'm going to set that to equal to 0, and that says that the optimal value of x is equal to lambda over 2. Okay, no big deal. So I can now plug that back into j, right? I'm going to take this, I know that's the absolute optimal value of x. I'm just going to plug it back into my original one to get this, right? Lambda squared over 4 plus lambda minus lambda squared over 2. Those are my terms there. And now I take the derivative of that with respect to lambda to find the right value of lambda, and I find that the correct value of lambda is equal to 2. And now I plug that back all the way up to here, right? Because I know the optimal value of x star is lambda over 2, and lo and behold, I get x star equals 1. So what have I done here? The basic, the function itself that I was trying was this, right? That's the x squared, and I'm trying to find the minimum point, but I want the value, it has to be on this side of this line, right? So it's going to be there. This is a line 1. So the right answer is going to be when x equals 1. It's on the boundary, right? Trivial example, but this is how it works. Now, let's look at what that actually looks like. So I plotted out this function. Let me just write this down. So this function here, x squared plus lambda times 1 minus x, okay? So here it is. Here's x squared plus lambda times 1 minus x, okay? And there's lambda, here's x, okay? So, and just over this range. So what do? You get a saddle function, right? So when lambda equals 0, if I set lambda to be 0, this term just drops out, and just x squared, right? So here, this is the lambda equals 0 term, right in there. And the minimum value of x is going to be, right in the middle. It's a little hard to see in 3 dimensions, but it's going to be there, right? The thing is just going to look like a parabola around 0. No big deal. Now, if lambda, now remember the optimal value of lambda turns out to be 2. So if lambda becomes negative, and it's not allowed to be negative, lambda always has to be positive. But suppose lambda is negative, what happens? This thing sort of drops down. Because what lambda being negative does is it flips the constraint, right? If I allow lambda to be negative, that means that x being negative is better. And as soon as x is negative, then the right answer is sort of at 0. And then after a while, it's to make x bigger and bigger and bigger negative values, right? So now x will go down to infinity. So you don't really want that. But let's think of what happens as lambda becomes more positive in this direction. So you'll see I get these curves. And what you'll see is that the minimum value is kind of tracking this way, right? The minimum value for x. So if the minimum value of x is 0 there, and it becomes 1, it might become 2 here, right? The other thing that's a little bit hard to see is that in the lambda dimension, there's a saddle like this. So I want to find the minimum value of x for each value of lambda. But once I do that, the maximum value of the cost, so this is the cost function, right? So the minimum of j the minimum over x of j of lambda gives you some value along here, right? But if I look at the maximum over lambda of j of x star, what happens is that looks like this. So that's why, so it's a saddle function. And the point is these Lagrange functions are always saddle functions. It will always, they always have that property. So they will always, and again, you can see what's happening, because this is just saying here, the further I am off the constraint, this becomes bigger if I go off the constraint, and this thing becomes, but I want this to be smaller. So so that's the structure of the one-dimensional problem. In the high dimensions, it's harder to think of it this way, but again, this is what's, but in the higher dimensions, you want to think of it much more in this sort of way, where what you want is this other thing that's going on. So this is the saddle point, where what you do is you find the minimum over x of j and then the maximum over lambda of that, and that will find you that saddle point. So the cost always goes up the highest point in lambda and goes down in x. So you want to find the best x for the largest lambda. Why the largest lambda? Because the lambda is telling you how much you care about your constraints. So I want the largest x. I want the value of x that solves the problem when I care the most as I possibly can about my constraints. So I want the big value of lambda, because that says I care about my constraints. I want to follow the rules. Lambda is how much you're going to follow the rules, right? So I want to be able to follow the rules as much as possible while still getting the smallest possible answer. So these are different ways of thinking about the same kind of thing. Now, here's another way of thinking about it. So again, let's go back to, now let's look in the high dimensional case here. So my Lagrange function, again, I have, not calling it J0 of x. Maybe that was, that's my initial, maybe that's x squared or something, or because we're now in high dimensions, maybe that's something like x transpose x, right? This is still a scalar function, right? This L is a scalar function, just like J is a scalar function, right? These are just numbers. But x is now high dimension. And now I might have many constraints. The number of constraints here is not the same as the dimension of x, right? I could have one constraint. I could have many constraints. It doesn't have to be in the same dimensionality, right? I could say in a 10-dimensional space, find the smallest point for which the first dimension is greater than 1, right? That's a single constraint. Or I could say find the closest point that is no closer than 1 from the origin. That's still a single constraint, right? Or I could say find the first point is no closer than 1, the second point is no closer than 2, the third point is no closer than 3, and now I've got lots of constraints. So you could have multiple constraints. So each of these is one constraint. You have a different Lagrange multiplier for each constraint. Now the Kuhn-Tucker conditions say, what do you want to do? You look at the gradient with respect to x of that, and we're ultimately going to set that equal to 0. And then you're also going to take the gradient with respect to lambda. The Kuhn-Tucker conditions are the combination of these two. The gradient with respect to x is 0, and the gradient with respect to lambda is 0. Remember, this one you're trying to find the max, that one you're trying to find the min. But the point is, those are both inflection points, so that, again, standard calculus, take the derivative, set it to 0 when you're trying to find extrema. Okay. So let's just look at this one here, which we're going to set to 0. What have we done? We've got, this is the gradient of the cost function that you care about. And this is the gradient with respect to x of the constraints. And so what you're basically saying, for that to be equal to 0, what does this look like? So suppose it was just one constraint. So suppose it's just lambda times gradient of c of x, where it's just one constraint. And I have here a delta of j of x plus that equals 0, right? So in some sense, delta j has to look like the negative of lambda of delta c, right? So what it's saying is that the gradients, one gradient has to look like a multiple, just a scalar multiple of the other gradient, right? Because now remember, delta c is still a function of x. So this is a vector, and and this is a vector, right? This is, you know, dj dx1, dj dx2, dot, dot, that's one vector. And this is dc dx1, dc dx2, and so on, right? And one has to equal the negative lambda, where this is just a scalar, times the other vector. So what does it mean when one vector is a scalar multiple of another? It means they point in the same direction with different magnitudes, right? So that's what I was talking about back here. The gradient of the constraint and the gradient of the cost have to point in the same direction. They're allowed to have different magnitudes, but they must point in the same direction. Okay? And lambda is the thing that says what's the relationship between those two different, what do I have to multiply by to get them to be actually equal? In this case, they're equal in opposite directions, but it doesn't matter. The point is that they're tangent at that point, right? So this is another way to think about it happening in higher dimensions. So again, it's because it's hard to conceptualize what's a saddle point in a high dimension. But the reason it's negative is because that's what it means to be a saddle point. The gradient of the cost is going down. The gradient of the constraint is going up. But at that moment, they touch. Okay. So, and these are it's just a condition, right? It's like this is necessary but not sufficient for optimality. But that's ultimately a good way to think about these things, right? Is to really think about what happens, what really the Lagrangian does is that this gradient with respect to x, setting that equal to 0, forces the two gradients to be in essentially the same vector, to be pointing in the same direction, and forces there to be a point of tangency. Does this make sense so far? Questions, concerns? Let's see. Somebody asked, what are cost function isolines? If I'm looking at a cost function here, j of x1 and x2, that's x1, that's x2. If this is the optimal, this might be, let me give a particular example then. Let's suppose that the cost function is x1 squared plus x2 squared, right? So everything in a circle has the same cost. These are, every point here has exactly the same cost. Every point here has exactly the same cost. Okay, so these are just the lines of same cost. The way to think, it's the same thing as a topographic map of a mountain, right? If you're trying to climb some mountain, you know, you can say, okay, what are my topographic lines along that mountain? What are the points of identical height along the mountain? So these are the points of the lines of identical height on a cost function. It's actually an upside down mountain, because usually we're trying to minimize costs. So it'll actually be like that in 3 dimensions, and we'll have circles or ovals of identical costs. So those are sort of the isolines of those things. Okay, so other questions? And I'll try to keep an eye on the chat here when people send these things in. So again, the Lagrange multiplier method is a trick. What the lambdas are necessary because these gradients may not have the same magnitude. So you need the lambdas to do that. Now, when there are multiple constraints, what you're saying is that if I sort of, I'm looking for a point that's in some sense tangent to all the constraints at the same time. Right? But here's a thing that becomes very interesting when you start looking at these things, which is some of the constraints aren't actually active at a given time, right? So this occurs when you're actually at the boundary. But suppose I have 2 different constraints. So get rid of some of this stuff here. Suppose that I've got my cost function like this. And I've got one constraint that says I need to be here. And that gives me that optimal point. And I have another constraint that says I need to be here, right? So the optimal point for that constraint alone would be there, but the optimal for both constraints together is actually here. right? Because this one, that point satisfies this constraint. It's in the safe zone, but it's the best point on this one, right? So what often happens when you start optimizing these things is you find that a lot of the lambdas are actually going to be 0. And in the extreme case, only one constraint will matter at a time. And if constraints are lines, that's usually the case. I mean, if you think about it, or hyperplanes, right? When there's usually only one hyperplane that is in some sense closest, right? Because again, if I do this, if I take a, again, you'll see this in 2 dimensions. If this is my cost function, and I start drawing constraint hyperplanes wherever I want, right? I can just ask which of these hyperplanes has a tangent that's closest, that's the smallest tangent. It's going to be this one, right? Now, this is an unsolvable problem the way I drew it there. Let me make it a solvable problem. I need to make it a solvable problem. Apologize. Let's do this, and we'll make a solvable problem like this. And all of these things, you always have to be to the right of them. You know, so these are the acceptable zones on all of these things, right? So there's only one of these that's close. So only one of those matters. And it'll turn out that the rest of the lambdas you can set to 0. And remember what I was saying before is the key to this whole thing is recognizing that most of the lambdas are going to be 0 most of the time. I haven't told you how you find these lambdas, but this is in most of these cases when you have multiple constraints, particularly when they're lines, this kind of thing is going to happen. Yeah. Okay. So back to what's going on here. When we look at once you found this, so now let's suppose we do this for the weight case, okay, and that's what Haken does. He goes through these things, and let me see if he finds his answer. He uses the Kuhn-Tucker conditions that you've got here. In this case, he's taking the derivative both with respect to the weights and the offsets. That's fine. And you'll find that once you do this, you get this is the answer for the optimal weights, and which is in terms of the alphas, which he uses alpha instead of lambda in this case. So in terms of the Lagrange multipliers. And now the only question is, can you find the alphas? There's also a constraint on the alphas here. And the question is, can you find all this? And then he goes back through how you'll actually find that. But before we figure out how you find the alphas, this is the answer. And remember, back up here, what does this look like? When I did this here, first thing you did is use the Kuhn-Tucker conditions to take the derivative with respect to x, and you find the best x in terms of the lambdas, or in his case, he's using alpha for that, right? Then you find the best alpha, and you plug it back in to get the best value of x. So what he's doing here is exactly the same thing, just in the weight domain. He's finding the best weight in terms of the alphas, and then later on, he's going to find the best alphas and use that to solve for the correct value of the weight. Okay, but look at what this expression actually is. Di is equal to +1 or -1, right? Di that's the answer, right? That's the correct value, and xi is the input. So we've got some input to my network xi, and I've got some output that I want to get, which is di for each value of x. Now I is indexing the examples, right? These are each example. So those are that's my network, and I have this additional sort of weighting term here, alpha I. Well, what did we do in the perceptron algorithm, right? In the perceptron algorithm, we said, okay, delta W is equal to di xi, right? We would just add, if we wanted x to point positive, we'd add it. And if we want to point negative, we'd add the negative of it, right? And you just do this a lot. So if we did this a lot for a fixed number, and I added up, and I did this for all, at the end of the perceptron algorithm, I have sum of di xi, right? In fact, the perceptron is a little cleverer than that, because it said you only do this when it makes mistakes. But you can think of it as adding a lot of these things in. So what's happening here is, if you were to think of it as a learning algorithm, it's like a weighted perceptron. Now, remember I said, though, that a lot of these alphas are going to end up being 0. So it's a really weighted perceptron. It's like a perceptron where you say, okay, I'm going to ignore a lot of the data. I'm going to select the data that are most helpful to me. And the perceptron algorithm itself does that a little bit. What the perceptron algorithm says really is, it doesn't actually say this. It says we're going to take the sum of dixi only if sigma of W transpose X does not equal di. So I'm only going to do that on the errors. So I'm already selecting, I'm self-selecting, right? I'm saying if I'm not making an error, I'm not going to learn. What does that mean? And again, this is just to give intuition. This is not exact. But what that means is that up here, if my line is already here or close to that, and this term comes in, I'm not going to make an error. It won't affect my line at all. The only thing that are going to affect the line is things that come in that are sort of on the wrong side of it. And those will pull the line in the other direction. That's how the perceptron algorithm works. So the perceptron algorithm is not that far from SVMs. And you guys noted when you tried to simulate this that the perceptron algorithm, you know, in our 2 half-moon case, did a better job of finding the line here than LMS, which often did that, right? So the perceptron algorithm actually does a pretty good job of what the support vector machine is trying to do. It's not perfect. It cannot be proven to be the same thing, but it's not as far off as you'd think. Okay, so that's worth being aware of. And that's what I was trying to point out here. Alpha I is 0 if xi is not a support point. So this, now again, you don't know these alpha i's in advance. You have to get all your data in before you can figure this out. Okay. So back to Haken. So what's happening here? So again, I said this is the W's in terms of the alphas, but it hasn't said how you're going to find the alphas. Okay, so that's the W. So now you're going to. So now we're going to do this in a Lagrange multiplier framework, right? So what's the Lagrange multiplier framework again? This is the network output. We want the network output is +1 or -1. So we want the network output when multiplied by the desired network output. So this is +or -1. That's +or -1. We want, when those things multiply each other, we want them to be +1. So this is our constraint. That thing -1 should equal 0. Right? So it's actually an equality constraint. It's not a less than or equal to, right? But again, as I said, it doesn't matter. All interesting solutions always lie on the boundary. And just as in any good Lagrange formulation, we multiply our constraints by this. Now, this is interesting because you think, wait a minute, I thought the cost function was the error. So far, we keep talking about the cost function being di minus W transpose X. It's this, right? Being expected value of that thing, right? So wait a minute, wasn't the cost function the squared difference from where I started, right? And here we say, no, we're going to call that a constraint. We're going to say we're going to constrain you to perfect behavior. You're not allowed to have any imperfect behavior. The behavior is the constraint. Our cost function here is just going to be this, the size of the weight vector. We want a small weight vector that does this. Okay. So that's kind of turning things on its head a little bit. It's like, wait a minute, because if you think about everything up until now, we started out with a cost function, which is the error on performance of the network. And we always take the derivative of that cost function with respect to the weights, right? We would always take dj, dw. Now we're taking a cost function, which is just the size of the weights. It's not about the error. We put a constraint that represents the thing we care about, the output of the network. We create the Lagrangian out of that. And now we take the derivative of that with respect to the weights, the Lagrangian, right? But it's not the same thing as what we were doing before. So I want to make that very clear, even though the terminology or the variable names tend to be the same. Okay.
Can I ask a question?
Sure.
Why do we want to minimize the size of the weights?
Good question.
Is it just so it's less complex?
Well, there's a number of ways to think about it. One of which is that just the cynical one is just to get us a unique solution, right? Because what if it would have worked just as well if we tried to make the size minimize W transpose W minus 3 or something, right? That would have been pretty, you could have said, I want the size of the weights to be 3. You could have done anything. Why? But this is the way Haken justifies it. And it's not a bad one. So here's my separating hyperplane, and I've got points on both sides of it. Now, but let's sort of look numerically at what these things are. So I could have a separating hyperplane that is quite far from these points, or I could have a separating hyperplane that's quite close to these points. The W magnifies this. So W is actually the points in this direction, right? So W, this is the value of W transpose X, and it says, so W says which way do I go off that hyperplane, right? If it's positive, I go this way. It's negative, I go that way. If points are very close to this hyperplane, you need a big W to get all the way to 1, because I want W transpose X greater than 1. And here in this direction, I want W transpose X less than -1. I'm going to sort of set I want it to get somewhere, almost like it's not a strict cutoff there, but there's a little bit of, sort of a no man's land in the middle here. And I want to get to one side or the other of it. So if I allow W to be very big, I can correctly distinguish points very close to my hyperplane. The smaller W is, the farther the points have to be for me to be able to really separate them. So small w means points are far from the hyperplane. If I can solve this with a small w, it means that I don't need a microscope to figure this out. But if I allow w to be big, it says, well, hyperplane's not so hot because yes, it does a separation, but I kind of need a microscope to see it. Again, it doesn't matter as much as you think because there's scaling factors, right? I mean, there's also, are we doing this in radians or degrees or furlongs or inches or centimeters, right? There's all sorts of scaling factors that you don't know about. What is one, one what? 1 mile, 1 micrometer, we don't know what these things are, right? So there's all sorts of scaling factors, but the point is that the smaller W is, the further your points can be, and you can, for any scale, the further your points have to be from the plane in order to be able to solve the problem. So that's where that's coming from. Does that make sense? Okay. So, and again, this is a construction, right? This had to be built. This is not some general principle of Lagrange multipliers. This is the way in which support vector machines are constructed. Now what happens is that you could take that. Now we're going to construct the Lagrangian, and he just multiplies out all the various terms. And there's a couple of things. You'll notice that we already, from the first conditions, we already knew that sum of alpha I di equals 0, so that allows you to get rid of this term. So now, so now we can sort of write this out. And remember, we're going to essentially take the derivative of this and set it to 0 in some way. But before we do that, we're just going to write out. We're just going to try to solve for this thing. So what we're going to do is we have that, and we also know what the correct value of w is supposed to be in terms of the alpha. So we can plug it in, right? We plug this in and we plug that. So we can take that correct value of w and we can plug it in. We can find it comes out to this term here. So we can plug that in for this. I forget exactly why, but this comes out to be 0. Let's see, the third term is 0. We have this. I see they're equal to it. That's why. So these two terms look very similar to each other. The half makes this thing come out to that. And then what you have left when all the dust is settled is you get this term here, which is now only in terms of alpha. We've removed the weights, right? We basically plugged this value in for the weights. And so now we have a function only in terms of alpha, right? And now remember, so we've already satisfied delta, the gradient with respect to x of j equals 0, because that allowed us to plug in for w. So now we need that the gradient with respect to alpha of j equals 0. So the first thing we've done is we found j of alpha given and the optimal x, and we're going to call that thing q of alpha. And now we're going to try to take this, which basically means we're going to do the gradient with respect to alpha of q of alpha, and set that thing equal to 0, and that will allow us to optimize this thing, and that'll find the alphas. Once we have the alphas, then we can go back and we can plug in and get the w's, and we're done. Remember, it doesn't look like a learning rule, right? It looks like it's an optimization parameter, and we still have to optimize. I mean, you still have to say, what are the alphas that maximize this thing, right? So you have to max over alpha of q alpha. Sorry, it's not, doesn't like doing, oops, that's because my pen shut off, that's why. Of q alpha. So you still have to solve this problem. And again, you may be able to do that by literally finding this gradient and setting it equal to 0. Sometimes you can, sometimes you can't, but there's a bunch of tricks that allow you to do this. Okay. So this is called the dual problem. Why is it a dual problem? So what do we mean? You see these words primal and dual, you know, primal versus dual. So what do these things basically mean? In general, there's no universal definition of what these things mean. An example of primal and dual things is that I could have the set of values x, and I could have the set of functions f such that f of x is a function, right? And I can think of y equals f of x as something that takes x and transforms it into y, right? According to function f. But I could also think of it as something that takes f and transforms it into y because of x, right? The same thing, right? So I could pick, so the point is that often you'll say things are like the primal space is the data and the dual space are the functions that operate on it. Yeah. Another example of primal and dual spaces is anytime one thing multiplies another. So if we have the inner product of w and x, we can think of that as w as some function of x. W of x is equal to w transpose x, and we can also think of it as x of w equals w transpose x, right? So each one in some sense operates on the other, but they are but essentially they live in very different spaces, because you can define an inner product where these things are in different spaces, where x is an element of some, you know, I don't know, could be the real numbers, and this thing could be in the complex numbers, right? So that's a perfectly valid thing. They could live in different worlds. Just the way f here, these could live in Hilbert spaces, and that could live in the real numbers or real vector space. So primals and duals can be that kind of thing. A place where this occurs a lot is if you look at things like the delta rule for backpropagation, and you'll notice that what you often get is you get these terms that look like delta w equals delta x, right? Where the deltas are coming backwards, are being backpropagated, and the x's are being forward propagated. This delta x it behaves a little bit like an inner product. It's not exactly like that, but it looks like one operating on the other, right? And creating this. And so in some sense, the deltas coming back are the duals of the data going forward. So the data goes in one direction and the errors come back the other way. That's another primal dual example, right? Where you have these things that sort of interact, and usually there's some kind of multiplicative interaction that happens between them. So, these are just examples of things that people might talk about being primal versus dual space. And it's used in different ways in different contexts. But it means that there's usually two different things, two different categories of things, each of which can somehow act on the other in some way. So in this case, what we're looking at is we have the x's in the primal space. Well, actually, in this case, the primal space, I'm sorry, is the w's. W is in the primal space. Those are the weights, are primal. And the alphas are in the dual space. And again, if you look at it, there are these terms, like here, there's always an alpha multiplied by something that has to do with the weights. So there's always some kind of, they're always sort of acting on each other in some way. And, or in the general Lagrange formulation, you're going to have a sum of lambda I times constraint I, which applies to x, which you can think of lambda as a vector inner producted with the constraints as a vector x. So here's your product formulation. These things live in different spaces. These are sort of functions. These things are these things are real numbers or vectors. So they're operating on each other. So you can think of these as primal and dual spaces. Again, so in the Lagrange formulation, what you're doing here is you're solving an optimization problem in the dual space. Now, that can sometimes be easier than in the primal space. Not always, but for many of these cases it is. So here's what's happening here. When we look at this function, we get this kind of thing here. And there's a couple of interesting things about this to notice. There's this xi, xj. What are those xi's and xj's? Those are all, that's your entire data set, right? If you looked at the sum of xi, xj outer product, that essentially is equal to the expected value of xx transpose over your data, you have to multiply by 1 over n or something, but that's the sample expected value. That's your autocorrelation matrix, right? This is the other way. This thing's a scalar. It's x transpose x, right? So it's actually a scalar, but again, it sort of has that same flavor, right? You're looking at the ways in which these things correlate with each other over your entire input space. But remember, I said that a lot of these alphas are going to be 0, right? A lot of those constraints don't matter, because you can optimize this. So remember, you're trying to maximize Q alpha, but alpha is allowed to be 0. So the optimal value may involve alphas that are 0. And that's going to be important when this thing is solved. I didn't tell you how to solve this thing, right? I just said, let's suppose there exists a maximum of this thing. Okay, so good. We don't have to deal with those things. When we do maximize this thing, so this is your Lagrange problem. Maximize that subject to this. What does this do? This is basically just balancing these things out. D is only equal to plus or minus 1. So the idea that alpha I di equals 0 just sort of says, okay, it all has to, either all the alphas are 0 or there's an equal number of them for the positive D's and the negative D's. Now, this term here has, that's the square of the number of examples, right? If I give you n examples, there's n squared of these things, right? But remember, a bunch of these alphas are 0. And if either one is 0, that entire term drops out. So this term only matters if both of the alphas are non-zero. And this is where you're going to get a lot of gain in this, right? Because you only care about the support vectors near. And the optimal weights only depend on the support vectors. Any alpha that's equal to 0 is going to drop out of this term too. Right? So this is why you get some kind of useful behavior out of these things. Okay. So let's keep moving here. There's this concept of these slack values, and this comes up in one of the homework problems, which is what happens if I'm going to say, look, I've got my dividing line here, and I got a bunch of points on one side of it, and I got a bunch of points on another. but I'm going to allow a few errors, right? I'm going to let there be a few errors, or things that are at least a little too close to this line. They're within my boundary box here, right? And they're going to be a little bit too close, and I'm going to allow that to happen. So what am I going to do to allow that to happen? I'm going to change my constraints. So I'm going to say, rather than forcing everybody to be some distance away, which is going to be a minimum of 1, rather than forcing everybody to be 1 away, I'm going to allow them to be 1 minus some epsilon I. So I could allow a point to be closer than this boundary. I still want it to be on the right side of this for the moment. But ultimately, if epsilon were, for instance, you see it's allowed to be greater than 0, this thing could actually be negative, right? That could pull you to the wrong side of the line. So how am I going to do that? So I'm going to put that in the constraints, right? So this looks like a constraint term. But what I'm also going to do is I want to say, look, I'm allowing that to happen, but I don't want it to happen that much. So what I'm going to do is I'm going to put this term here. I will say I want to minimize these. When the epsilons are 0, then I guess just get back to, then I have to be outside my external boundary lines there, right? I have to be at least this far away from my division hyperplane. When the epsilons are all 0, or for instance, if C is 0. But if I let C get bigger, as C goes to infinity, for instance, I'm going to allow the epsilons to be non-zero, right? So when C is 0, I say I just have to make the weights as small as possible. And let me think of the other. When C is 0, I want these weights to be as small as possible, which means I want these lines to be as far away as possible. But as C gets larger, I have this other term in here, which is going to say this stuff is more important. And it's basically going to allow my weights to not matter quite as much how big they are. So let me show you what that means here. When we solve for all of this, we end up with the same dual problem that we had before, subject to the same constraint. But before, we had alpha I was greater than or equal to 0. And now we have an additional constraint. We also have alpha I is less than or equal to this value C. Okay, so it's saying our Lagrange multipliers can't be that big. What does that mean? What happens when a Lagrange multiplier gets really, really big? Let's go back to the Lagrange formulation here. If a Lagrange multiplier gets really, really big, suppose that thing goes to infinity, it says you really have to obey this constraint, right? That constraint had better be 0, because otherwise I'm never going to minimize this thing. So if a Lagrange multiplier gets big, it says I really, really, really am going to follow the rules here. So if I put a constraint on the Lagrange multipliers, figure out where I was. Here we are. If I put a constraint and I say, no, I'm not going to allow these Lagrange multipliers to ever get that big. It says I'm not going to ever force myself to obey the rules that much, right? And the smaller C is so if C gets closer and closer to 0, then it says I'm going to, I have more and more of a constraint, right? If the bigger C is, the more I'm allowed to follow my constraints. The smaller C is, the less the constraints are going to matter. And so, but of course, the smaller C is here, then the less I care about the values of these epsilons, right? Because the value of 0 says epsilon can be anything it wants to be. So if epsilon can be anything that it wants to be, then I've completely relaxed the constraints, right? If I say this constraint, this D times W transpose X plus B is greater than or equal to negative infinity, I'm not doing very much, right? Everything's greater than negative infinity. So if I allow these to take on any value I want, right? Epsilons can be arbitrarily large, then it's as if there are no constraints. So that's what happens. If C goes to, let's make C, so C goes to 0 is the same as no constraints, right? Which is the same as saying alpha I equals 0. C gets very large, or let's say C goes to infinity, says big constraints, right? So if C goes to infinity, then there'd be a very big constraints, because what's happening, I'm penalizing these epsilons, right? C is very big, so epsilon is going to hurt me a lot in terms of my cost. So I want the epsilons to be small. Ultimately, I'm going to want them to be 0 if C is infinite, right? And that is the same thing as letting my Lagrange multipliers become very big, so I care more about the constraints, right? So the bigger C is, the more I care about my constraints. The smaller C is, the less I care about the constraints. So it allows you to say, well, you know, we're going to kind of follow the rules, but not so much, by letting C get small. So C is sort of like, you know, it's the strictness of your police. Okay. So that's an additional term that's added. It doesn't actually make a huge difference in how you solve Lagrange multiplier problems. Okay. There's a lot of talk about this thing called the kernel trick. There's a lot of ways to think about the kernel trick. The simplest way that I like to think about it is that now the kernel trick applies in the case where instead of this being a linear dividing line, I want it to be a curved dividing line in some way. And the way I'm going to do that is, rather than curving that, I'm going to take X and I'm going to run it through a bunch of nonlinearity. And then I'm going to take those things and combine them back through some weights, right? So now I'm going to have W transpose phi of X, just like we did, T equals that. And this is the standard, say, radial basis function network. The thing to recognize, though, is why does this actually give you anything useful? It gives you something useful because, remember, you only have to take the sum over the non-zero alphas. So the radial basis functions here, there may be a lot of radial basis functions, right? And so calculating this, you know, phi transpose phi can be expensive. And I have to do it for every single value of X. But in fact, I don't. I only need to do it for the ones where the alpha is non-zero. Now, what's going to turn out is the alpha is only non-zero for the constraints, and the constraints are only the support vectors. What do support vectors look like in a radial basis function case? Let's suppose that we've got the dividing line we want looks like this. So now my support vectors are going to be points that are going to lie sort of along my dividing line like this. And they're going to have little radial basis functions around them. But there could be radial basis functions everywhere else in this space. There's lots of these guys out here, right? Lots of other radial basis functions. But I could decide which side of this line I'm on. Draw it in red. I could decide which side of that line I'm on without paying any attention to all of these guys. They are not helping me, right? Because in the end, it's just as good if I have a function that is, you know, high and it just goes low like that, right? This function is just as good, right, as one that wiggles around on both sides of these things, right? Because all I want is this is all +1 out there and this is all -1 there. So the whole thing could be decided by these guys. And in fact, what I'm going to do is suppose that I have a new point that comes in here. I could put a radial basis function on top of it, but I don't have to do that. I could just take this and I could say, okay, look, these radial basis functions, they go on forever, right? I mean, these things are, you know, little Gaussians, they go on forever, right? So I could figure out, okay, what's the value here of this point, right? Of just these radial basis functions, right? Of just the ones near there. And I'll get some values. I mean, they'll be small, but it will be bigger than all of these guys because these guys are farther, right? This point is closer to this set of radial basis functions and further from these. And so everything out here is going to have bigger values for these guys than it will for these guys. And so we'll correctly classify. And I didn't have to put radial basis functions out here at all. I didn't need them. Okay. So that's where the kernel trick comes in, because the point is the kernel, which basically is just phi of xi, phi of xj, the sum of that over I and j. It's actually the sum over alpha I not equals 0, alpha j not equals 0, which is much smaller. And if they're radial basis functions, then there's as many of them as there are these xi's and xj's. It also works if they're not radial basis functions, but it's easier to imagine it in this case. Yeah. So that's basically how these machines work, is that it says, look, I don't need all this stuff out here. I don't need to remember those radial basis functions. I don't need to remember the data points. I'm only going to optimize. I'm only going to find the functions that I actually need to make this decision. Even when it's a curved decision, I'm only going to remember those basis functions, and that's sufficient to make these decisions. When you're doing this for continuous functions, it's the same thing. There's not decision boundaries anymore, but you only need to remember the things that are important at actually changing the value of the function. So remember that RBFs, what they typically do, remember we had 3 ways of allocating RBFs, right? So for RBFs, you could put them at the data points. You could do them based on the function, sort of backprop. Or you could, watch my time here, or you could do some kind of unsupervised and put them where the data is, so like k-means or something, right? You have 3. So here's a 4th one. You could use SVM, right? You can think of SVMs as a way of where do you put your RBF centers. And the SVM is very close to function, right? Because it depends on the function you're trying to do. But it's trying to be very sparse about it. It's trying to say, this is exactly where I need to put these things. And you can show that there are sort of backprop-like algorithms, just like I was talking about the perceptron algorithm, which is related to that, and there that will approximate SVMs. So I think I'm going to stop there. This is a very complicated chapter in terms of the way it expresses a lot of the math, although I think it's actually fairly good about it. If you look at most of the books that look at this, or even online stuff, they just sort of say, this is what an SVM is, now go use a package. It's and the thing to realize is that you can do this. These optimizations, when you're using the kernel trick optimization, all of these optimizations are non-trivial. This is the optimization you have to be able to do. But it's not. There are ways of doing that. Usually with this sort of nonlinear, depending on whether this is linear or nonlinear. In this case, the optimization isn't very hard. This is just a quadratic problem, and we know how to optimize these things and using an eigenvector expansion. But in the nonlinear case, it can be a lot harder to find these things. But in the end, even what the kernel trick does is it converts these nonlinear problems into linear problems. This thing here could be thought of as this whole thing looks like an inner product. And what you're basically trying to do is you end up trying to maximize things that look like V transpose Q V, where these are vectors and that's a matrix. The output is a scalar, and we can basically do this because the maximum of that always looks like V looks like the principal eigenvalue of Q, eigenvector of Q. So when you actually start looking at how you solve these problems for specific cases, they almost always succumb to linear algebra, and it's not that difficult. You can also you can sort of do it by brute force in a lot of these cases. You can just, because again, remember the first thing you have to figure out is which of any of the alphas are non-zero, and you can usually do that just by trying it. Okay, I'm going to stop there because we're a little bit over time, and see if you guys have questions.
Professor, can you explain the saddle point again?
Sure, let me show that picture. Here's my saddle point picture. Okay, which is this function. I just graphed out this function. Let me write it out again. We can do this. Jake will. Okay. j equals x squared plus lambda times 1 minus x. So you understand where this equation came from, right? This is the Lagrange multiplier, and this is the thing we're trying to minimize. And this is the one-dimensional, it's the following one-dimensional problem. This is x squared. And what I want to do is I have a constraint here. That's that, right? So I know the point is going to be that, right? I know that's going to be the optimal one, right? So, so lambda times 1 minus x, what does 1 minus x look like? It's a line that goes through here. And lambda times that changes the slope of this line, right? And I'm just basically adding those two functions together. Okay. And we also know, because we calculated it already, that the optimal value of x is 1 and the optimal value of lambda is 2. Okay. But you can blot this out. So let's take the value for lambda equals 0. What do we get? We get that. Now let's take the value for lambda equals 1. What's that? So that's x squared plus 1 minus x, right? And so we have to take this, we have to add 1 minus x, and what you're going to get is you're going to get something that looks a little bit like this. You're going to get a 0 that's out there somewhere. It's actually, it goes higher than that, I think. Let me try and actually plot this properly. So in this case, it's x squared. In this case, it's x squared minus x plus 1. That doesn't have any roots. So at 0, it's 1. And at 1, it's also 1. And the minimum is going to be somewhere in between there, right? It's going to look a little bit like this. Okay. Now let's take the case for lambda equals 2. I apologize, I'm not drawing this particularly well, but you'll get what I'm getting at. So now we have x squared minus 2x plus 2, right? So now at 0, this is up at 2, and at 1, we're going to get 1. This 1. And at 2, I'm going to get 4. I'm going to get 2 again, right? So now I get this. Okay. And when lambda equals 3, I'm going to get something that's going to look as 1, as 3. It's going to go through here, and you're going to get a point that's up there somewhere. And this is 1 down there. So what happens is that at each point, we can find what's the minimum value of x. The minimum value of x here is at 0. The minimum value of x is here somewhere in between. The minimum value here of x is 1. Sorry, I drew this last one incorrectly. It doesn't quite look like that. It actually looks like this. Okay. The minimum value of x is out here, is there somewhere. So let's look at, for each value of x, well, for each value of lambda, what's the minimum value of x? So here's, this is 1. This one's, so here, the value, the min value of x here is a little bit less than 1. Here it's equal to 1. And here it's less than 1 again, right? So if we ask what's the maximum value over lambda of the minimum value over x of j, right? That occurs here. That occurs lambda equals 2. You see? Because what's happening is that the minimum value of x is changing its position, but it achieves a maximum when lambda equals 2.
Yeah.
If I were to draw this in 2 dimensions, this is what I get, right? So this is at x equals 0, you get these different values. As lambda gets bigger and bigger, the position of the maximum value of x changes, but it first goes up and then starts coming down again. So what I'm trying to do is find this max min, the max over lambda of the min over x of j. Does that help?
Yeah, thank you.
Sure. Stop the recording here.